Right, I'm just going to test some of these because they don't quite. Hang on. The voltage gain of the circuit doesn't quite add up to what I'd expect it to be, so that's got a current gain of 72. This forward voltage this tester is giving is way off. At the higher currents it creeps up to this, but at the few microamperes this circuit's using, it's only about 90 millivolts. Let's test the P-type. So look, current gain of 36. This one's quite correct. I'm measuring about 270 millivolts. So obviously this pushes them at a little harder current than what my circuit does. Current gain of 36. Look at that, it's exactly half of what the N-type measured. So bear with me, I'm just going to do some maths. Right, so back to this germanium circuit. Playing around yesterday, had a few drinks and stuff, and it just wasn't quite right. I wanted to alter some values because a bit scribbled out now. I had like some real low impedance values in places. Well, I'd done that because the current gain of germanium's being lower. So bias networks and stuff, you have to have a greater amount of current passing through them to compensate for the greater amount of current that's going to come out of the transistor. And the same, so it's not massive amounts of difference, but there is difference. Obviously you then get leakage currents and stuff. But so I thought, well, what's the point of using germaniums in a circuit and then biasing them in a manner so they behave as silicons? So I went back, rebiased them with much higher resistors and stuff, and it was just way out. I was hardly getting any gain at all. I could hear quite a lot of distortion, and it just wasn't right. Anyway, whilst just, you know, removing components and just making sure I hadn't made a mistake on the breadboard, at one point all of a sudden it sprung to life. I was like, what was that? And I realised I was actually running with no feedback. So you can see the original circuit was using feedback back to the emitter of the first transistor, negative feedback. Well, I'd upped it to like 10k and put 22k across here, and there was so little gain. The circuit itself only had a gain of just over 1, so there was practically no feedback at all. And because of the low impedance load I had on the collector of this, which would have been this still with the load the output presented and no linearizing component in the emitter here, coupled with it was biased way out of spec. The bias was way too low. There wasn't enough voltage and stuff. It was creating some distortion I didn't want. Removing the resistor across from here sort of brought it back into life. So I had a think, messed about some values, and I've ended up with this, and it is brilliant because I've got much higher impedances. Look, 10k instead of 1k. 4,700 ohms instead of like 1k, or yeah, I think that was what I had, yeah, originally. And then obviously that was in parallel essentially with a 2k too. So at DC it was sourcing current through here and some through here until this transistor turned on enough to balance the voltage out. Way off. So yeah, now the front end's very similar. It's bias network. This just adds an additional amount of impedance to the input of the stage. Could do away with this capacitor, then the input impedance instead of being about 10k would be somewhere around 12k. But this, not only does it ground it AC, it also, any small amount of hum when this isn't running on batteries on, it's on a proper power supply. If there is any hum or noise on the supply, this is going to be an additional level of filtering, so it's staying. But the reason I was just crunching some maths, I'm getting a voltage gain of this circuit of slightly above 7. Now, you look at the circuit here, you think, well, that transistor there, with a resistor here of 4k7 and 10k here, should have a gain of at least 2. Then you look at this one, you go, well, there's 220 ohm there, 2200 there. Well, admittedly, it's 100k here, which is going to be seen as in parallel with this resistor, and then the impedance of load being driven, which on that amp is, looks quite as about 100k on that amp, so that makes 50k. Parallel with a 2200 ohm load is going to be about, I don't know, it's going to probably still be above 2000 ohms. So you'd expect to see a gain of maybe 9. So you think, well, hang on a minute, a gain of 9 times by a gain of 2 should give me a gain of about 18, and I'm getting a gain of about 7. So the current gain on this transistor is 37. Well, it's got 220 ohm load in the emitter, so if you crunch some maths, 220 times 32 is 7040 ohms. So this transistor here, without this resistor, would still see this is a 7000 ohm load. These two are in parallel. The two of them together in parallel come to 4100 ohms. So the collector resistor is lower than the emitter resistor. Now, obviously the gain calculations only hold true for the, say for instance you had an emitter resistor here of 4700 ohms and 47,000 ohms is a collector load. If you want a gain of exactly 10, the gain in this trans would have to be near infinite. Well, germaniums just don't have that much voltage gain. You got current gain, voltage gain. There's different kinds of gain a transistor stage can have. Now, admittedly, voltage gain is basically just an artifact of changing the current through an impedance, which obviously Ohm's law says must generate a voltage, but the transistor itself still has to be able to give you voltage gain, as it were. Now, if you was to just delete this resistor, have a collector load and measure the gain, you'd get a sort of rough idea of how much voltage gain this transistor would let you have, and the same with this. So this is going to be running a gain of less than 1. Even if this transistor had infinite gain, it would have to be less than 1 because its collector load is lower than its emitter load. So then subtract the amount of gain that you lose from this transistor having some finite amount of gain. I've not measured it, but the gain's obviously a lot less than 1. Now this transistor itself is going to be pushing a gain of hopefully around about 9, so that would give me why I have a voltage gain of about 7. I think what I actually might just go and do is I'm just going to probe these and measure, actually see what gain I'm getting here and then work out what gain I'm getting here. Right, so I did some measurements. Now they're not going to be the most accurate in the world because they were just done with the multimeter and a 1 kilohertz test tone, so I should say the AC measurement in this, it probably wants a bit of a lower frequency ideally. But yeah, so anyway, this is the input signal to the base of the first transistor. So 36 millivolts input, I was getting 29 millivolts output and a gain of 0.8, and this actually stands true across all the various different signal levels I fed it. So this was flat out, this was the full signal level coming in, 183 millivolts, 148 coming out, so they all come to 0.8. There's a slight variation of some figures after it, like 0.9, 0.3, whatever, but it's close enough to call it 0.8. Now the one that doesn't quite add up is this 10.8. Now this resistor's only 220 ohm and this is 2200 ohms, so they're 1 milliamp through this resistor. If all of it went through to this resistor, it would be 1 milliamp. Well, 1 milliamp through 2200 ohms is 2.2 volts, and 1 milliamp through 220 ohms is 0.22 volts. So that would be a gain of exactly 10. Now, as I said, this collector impedance, as seen by this transistor, is parallel AC of this resistor, and the input resistance of the amplifier. So I was getting some real strange readings. This one, I'd like to believe, gives me a gain of 9.5. So the 0.8 volts drive to the base, collector 9.5 volt. Sorry, 148 millivolts to the base, 14.08 volts. 1.408 volts on the collector, gain of 9.5. These ones gave me a gain of 10.8. So I'm just going to go measure the resistances, because if this resistor is, say, 10% above its stated value and this is 10% below, that would maybe account for those deviations of gain. But I'm going to say also some of it's down to the meter not liking the 1 kilohertz test tone. Well, I don't know, because yeah, they measure actually 216 and 2160, so again 10 times bigger than this one. Parallel the resistor, so I'm going to just put it all down to the meter reading being off. But anyway, the reason I like this circuit is, like I say, it's germanium. The whole point was it was meant to add some kind of germanium vintage transistor sound to the signal. Well, I'll put in a picture in a minute of a screenshot from my oscilloscope, and you can see on it you've got the fundamental peak at kilohertz, and there's a massive peak of second harmonic distortion, then a small peak of third, and then it's just pretty much noise after that. This turned out, after messing about, it was yesterday when I was messing about with values, I started noticing the second harmonic, and I just kept playing around different values until I got it as high as I could, whilst sort of minimizing the third harmonic. It was, you know, sometimes you get a slightly bigger second, but then you get a big peak of third. So this circuit here, as it turned out, seems to work the best. You might ask yourself, if this transistor is running at a gain of less than 1, why even leave it in the circuit? Well, first of all, it's adding some of the harmonics. I don't know if it's mostly here the harmonics are being generated, or here, or if it's interaction between the two, which is helping generate this big second but sort of keep the third nulled. So that's one reason why it's in there. It's adding to the sound of the circuit. The second reason being, it's allowing a much higher input impedance. If I didn't have this and was trying to drive this directly, then whatever's driving it would see a 4,000 ohm input. 10,000 ohms is more akin to what you'd call the low end of an input of a line stage. I've kept it relatively low to, because it's obviously in a coming from a desk and stuff, could be long cable runs. It's just going to help minimize any noise pickup. But you know, 10k is more than low enough, high enough for anything to drive, really. So that's the other reason why it's in there. And of course the third reason being, there's no phase inversion. The signal comes in this end, it comes out in the same phase as that, and if you only had a single stage, it'd be 180 degree out of phase. So yeah, I've decided this zero feedback circuit is the way to go, and it sounds brilliant. It's not hissing, it's not buzzing, it's not humming. It's incredible how well this is working, especially even just on breadboard. So yeah, I think I'm going to try and build something similar with silicon next, and see if I can't generate more third harmonics with that. This I kind of think in a single transistor stage with a bypass capacitor on here, low collector impedance, and then a stage here with running low gain, you know, low ratio between these two resistors. So most of the gain is going to be in the input stage, or do most of the gain in this stage, real low gain here, whichever way around works better. And hopefully that'll be more of a third harmonic. So yeah, anyway, that's a little update. Joy of playing around these things. I'd say to anyone, if you're interested in electronics, don't go messing about looking at all the maths, because you try and learn how a transistor works, and it is just page after page of some of the most complex bloody algebra you'll ever see. And you don't need to understand it, because even if you did do all the maths, it's completely pointless, because it's theoretical, as in, not that, oh, in theory it works, but in reality it doesn't. Not that kind of bollocks theory. That's people who say that, I just don't know what they're on about. As in, there's so many variations, minor variations in the value of resistance you have, in the gain of the transistor, you know, so many real world variations that you could work out to within millivolts, this perfect ideal gain and frequency response and everything you get from a transistor stage. When you actually try and run it, if you built two exactly the stages identically, there'd be such big differences. You know, if you start going to 10-point resolution, well, even a variation sort of 5 decimal places away is a huge variation to what you worked out, but in real life terms it's nothing. You know, if I'm working out gain to a volt and I'm getting gain variations between 2 stages down in the even millivolt range, just to 3 decimal places. You just call it, well, that's close enough. Real world, it doesn't matter. This is why discrete transistor stages all have little tweaky gain pots and stuff on them, and little tuning capacitors if it's high frequency, because there's so much variation between natural components and things that would affect it, like the circuit board tracks and that. Like, it's irrelevant. Don't worry about the maths. Pick up some breadboard, buy some of this on eBay dirt cheap. Get yourself some, maybe not germaniums to start with because they're a bit expensive, but just go and get yourself a bag of cheap transistors and stuff, a couple of battery packs, and play about. Cheap multimeter, some crocodile leads, and just some connectors, and away you go. If you are going to do all the experiments, I wouldn't have your best speakers on. Just buy a cheap pair of PC speakers or something and a cheap little amp, and until you sort of are confident with what you're doing, then you can start seeing how your systems sound on your more high-end system. But just say to anyone, get involved. Don't worry that you don't understand it. The best way to understand something is to try it, fail, figure out why it didn't work, try again until it does work. But that's just my little motivational speech. And as always, thanks for watching, and catch you next time.